First, we'll use a trivial example to illustrate how Bender's decomposition works. In this example, the graph consists of 5 nodes, and the density of the graph is set to 0.5, meaning that only 50% of the arcs are feasible. The graph is represented by two matrices that are 5 by 5 in size. They represent the upper and lower bounds of the arc length. Each element in the matrix represents the arc length between node I, which is the row, and node J, which is the column. I want to draw your attention to when the arc length is set to 10,000. It means that this arc doesn't exist, and it has so much resistance on it that the algorithm will never pick it. The source and the destination nodes are arbitrarily set to node 1 and 5 respectively. Matrix Y contains the binary decision variables of whether an arc is selected to be on the robust shortest path or not. It is initialized as a zero matrix, basically saying none of the arcs are on the robust shortest path. The procedure of the Bender's decomposition goes like this. We will go through it step by step using the simple example. First, the objective function value is set to negative infinity. Then we solve the subproblem, which is shown on the right. Since y is fixed to be a zero matrix, the first term of the objective function is 0. The second term can be simplified to just L times W, like this. This becomes a trivial problem, and the solution can be easily found through simplex or even just by inspection. The resulting matrix and objective function value of the dual is shown below. Now we move to the next step, which is to compare if z is larger or equal to the dual cost. If that's the case, we have found the best solution and we can exit the loop. Unfortunately, z is negative infinity right now and the requirement is not satisfied. Now we check if the subproblem was unbounded. In this case, it was bounded and we even found the optimal solution of W and the dual cost. So we skip the next two lines and go directly to the else statement. We have a new extreme point, which is matrix W on the right. Also, we add a new cut to the master problem. The next step will involve solving the master problem. The first constraint is the cut that we just added. And we do this for every W in PR. PR is the set of extreme points. As of now, we only added one extreme point to PR, and that was during the last step. The next three constraints are concerned with node flux conservation for the source, destination, and the intermediate nodes. This is again a trivial problem that could be efficiently solved, and the results are like this. So how do we interpret this result? In matrix Y, elements Y13 and Y35 are set to 1, meaning that arc13 and arc35 are chosen to be part of the robust shortest path, and the corresponding Z value is 0. Now we go back to the beginning of the loop and solve the subproblem again. Since matrix Y is fixed, we can simplify the objective function just like last time, like this. The solution can be easily found as shown below. The dual cost has been updated from -7 to 20. Now we ask ourselves if z is larger than the dual cost. No, it's not, so we need to continue with the iteration. Then we ask if the subproblem was unbounded. No, it was bounded, so we can skip the next two lines. So we have a new extreme point and a new cut, just like last iteration. Now we solve the master problem again. This time we have two extreme points in set PR, and z needs to be bigger than both of this constraint. The solution to the master problem used to a matrix and an updated z value of 20. Now we are in the third iteration of the subproblem, and the subproblem was solved again. We have see that there is no change in the solution compared to the last iteration. Now we ask ourselves if z is larger or equal to the dual cost. Finally, they are equal to each other, and we can exit the loop. The scenario described by matrix Y is the optimal decision variables of the robust shortest path, and the corresponding Z is 20. After having the simple example in our pocket, the rest of the project will just involve coding Binder's decomposition and use it to solve large-scale problems that are perhaps not so trivial.